Log on, tune in, find out. Another good idea from Cambridge.
Florida State University, and I think that title's changed. Inviscid dissipation catalysed by topography. It's all yours.
Something like that, right? Yeah. So it looks a little washed out. I don't know if is that visible to everybody? Okay. Well, we'll see. Maybe things will get better. First, I want to take this opportunity to thank the organizers. Professor Huthmans was the person who first contacted me about coming. I don't think he's here, but anyway,
No, this week.
Okay, I did want to acknowledge him and thank him for inviting me to come. It's a very great honor to participate in this summer school, and to thank the committee of organizers in general, because I think this school is actually providing a valuable service to the fields of GFD, oceanography, meteorology, climate sciences, broadly speaking. So it's a very valuable service, and thank you very much. Today, what I would like to spend a little bit of time talking about is some work that I've done lately that has to do with the question of, I'll motivate a little bit later, the issue of energy dissipation of the balanced flow, and I'll explain what I mean about that. Now, yesterday we had a very nice seminar that was entitled something like Predicting the Unpredictable, which of course is quite implausible sounding. I have an equally implausible title here, Inviscid dissipation, catalyzed by topography. Those two first terms are somewhat inconsistent with each other. I can only hope that I will be able to be as eloquent as yesterday's speaker to present something which may convince you that the terms are not completely crazy. This is work I've done actually following in the footsteps of some brilliant collaborators that are listed here, some of whom I believe you should be very familiar with. Pavel Burloff, sitting here in the first row, has been a stalwart, the third row, excuse me, has been a stalwart of the team. Andy Hogg from the Australian National University has also been integrally involved in this effort, as has our very good friend, Professor McWilliams of the UCL&A. This is my uvažimija kolegija, and this is my good mate. So, I would also like to say that I got interested in this problem, broadly speaking, many years ago on a very pleasant sabbatical visit to Oxford at a time when Peter Kilworth is there. So in many ways, the inspiration for this work comes from that collaboration. So I offer this in memory of Peter Kilworth, who passed away a few years ago. The field sorely misses him. So, how does one motivate this? Well, typically, you go to many of seminars, you'll see people running global simulations these days. Here's an example of the kind of output that you get. This comes from the HICOM model, Hybrid Coordinate Ocean Model, run by my colleague at FSU, Eric Chassagnier. What we're looking at is sea surface temperature at a particular day. You see a number of features in here, like cold upwelling along the coast of South America. There is evidences here of a Gulf Stream front. There is a Kuroshio front. If we were to take a number of quantitative measures of the behavior of this model and then compare them to what we think we know from observations, there would be, to my mind, an admirable agreement between the two. I think the state of the art of global simulations has really come a long way, and the people who do this are to be congratulated for their successes. But there are a few things that are yet in need of some attention in these models. What's not seen, what they largely calculate for us is something that I'm going to refer to as the balanced flow. That's, roughly speaking, flow that has a diagnostic set of momentum equations at leading order. It's defined by a potential vorticity field, which is intimately connected to the dynamic fields associated with the balanced flow. That's all these models are capable at the moment of calculating, given the scales that they work at. Now, it turns out that we know a fair amount about the energetics of the balanced flow. That's something that has been looked at by a number of people. Here's an example of one analysis due to our very good friends Professors Wunsch and Ferrari at MIT. This has recently been updated, but nothing has substantively changed in this wire diagram. What it's describing is the energy flow in the ocean, which, because the balanced flow is the primary largish scale flow in the ocean, including such things like the Gulf Stream, the Kuroshio, mesoscale eddies, so on and so forth, it primarily involves the energy flux through the balanced flow. Their analysis argues that the primary sources of energy for the general circulation are the wind. They argue here that heating and cooling doesn't really add any energy. This is a point of some contention, but it seems that the primary driver of the general circulation, general balanced flow, the winds. And the rate at which this energy is provided to the general circulation is approximately 1 terawatt. Now, what's a terawatt? I don't know. It's a whole lot of watts, let's say that. But, you know, rather than worrying so much about the absolute value of it, the issue is the flux through the system. So we get a terawatt into the general circulation. This is the broadest scales of circulation in the ocean, the general circulation of the North Atlantic, the Antarctic Circumpolar Current, etc. By and large, those flows are in some kind of equilibrium, so we're about losing 1 terawatt from that. Now, we know how that happens. That happens through geostrophic instabilities for which there's a well-developed theory based on geostrophic dynamics, quasi-geostrophic dynamics being the best known. So the general circulation is both barotropically, baroclinically unstable. It gives up its energy at a rate of 1 terawatt to mesoscale eddies. And that's what's shown by this aspect of the wire diagram. A bit of loss to dissipation of the general circulation, and about 0.9 terawatts goes into the mesoscale eddy field. Now, it's at this point where the picture becomes a little less clear. We don't really know what happens to that energy. It does appear from several decades worth of observation now that the mesoscale eddy field is not itself accelerating, so we must be losing about 0.9 terawatts from the mesoscale eddy fields. How that happens is a subject of some debate at the moment. There's a possibility that the mesoscale eddy field is directly unstable to internal waves. That would be useful. A mesoscale eddy field has the properties that it wants to flux its energy towards larger scales and therefore away from the scales at which dissipation is directly effective. Internal waves don't have that property. So if you can destabilize the mesoscale eddies to the internal wave field, then you can flux energy and therefore eventually to dissipation by this pathway. But there are lots of reasons to think this may not be actually happening with any great efficiency in the open ocean. So the direct route to internal wave excitation doesn't appear to be too promising. There's open ocean dissipation, but again, as I've argued, that looks as if itself is a very weak process. So kind of by elimination, what we're then left with is the option of boundary dissipation. Equivalent to saying, since internal mechanisms don't look like they're very effective at draining the energy out of the balanced flow, perhaps some external influences come into play. And the obvious external influence that comes to mind is boundaries, topography, the bottom, etc. So this is the pathway that I want to examine to see if it makes any sense, if it's at all possible for the mesoscale eddy fields to actively be losing their energy from the balanced flow into something which can then be dissipated. And if I didn't have anything to say about that, I guess I wouldn't be here talking to you today. So the point is I'm going to argue for a mechanism here that I think is promising. Okay.
Excuse me a moment. You shouldn't leave us with the impression that interaction with topography is a completely separate thing from generating internal waves.
Of course not. There are people who have looked at the question of mesoscale flow over bottom topography, rough bottom topography, and have found that that's a mechanism by which internal waves can be generated. What I was talking about here was the spontaneous emission of internal waves by geostrophic balanced flows in the interior of the ocean away from external effects.
All right, that's much weaker.
Okay. And, okay, now I'm going to be skewered, so everybody be prepared for this.
Can you remind how this diagram, they distinguished between bottom dissipation and boundary dissipation?
Mm-hmm. Why do they do that? Well, because, sort of qualitatively speaking, rubbing over a bottom itself has got a certain intuitive picture that comes with it. Rubbing up against lateral side boundaries brings a different picture to mind, so I think they're just kind of drawing a distinction between those two. In some sense, it is rubbing up against the bottom always. Okay, now there's a related potential vorticity budget question. This energetics question has several ways it could be addressed. There is a potential vorticity question, however, that cannot be addressed in any other way. That's something that we know from the Haynes and McIntyre analysis of potential vorticity, which shows that it cannot go through potential density surfaces. We recently, in some work I did with a graduate student, have had a look at the net injection of potential vorticity onto particular isopycnals in the North Atlantic that occurs at the surface. In long-term average, that appears to be non-zero. Now, since we have to have an approximate budget balance of potential vorticity, as well as in energy and everything else, that implies that you've got to get that amount of potential vorticity out of the flow, and the only place that that can happen is at the boundaries. So that tends to be an issue that's strongly connected to energetics. In quasi-geostrophic theory, potential vorticity and energetics are essentially interchangeable. The connection is a little bit more elaborate if one goes to things beyond quasi-geostrophy, but nonetheless these two issues are somewhat related. And I wonder if there's a connection to the theme of this school in the sense that a lot of models, especially those used in climate, really do not calculate the mesoscale field. And to the extent that the mesoscale field is going to be integrally involved in the dissipation processes that control the amplitude of flows in the ocean, you would like to parameterize those, and you'd like to do that in some kind of dynamically consistent way. The mesoscale field is something that's perhaps easily thought about as a stochastic, something that you could model with a stochastic forcing or a stochastic dissipation. And I'm wondering if what I'm going to be talking about here is the basis for some kind of stochastic parameterization of dissipation in oceanic components of climate models. Okay, now, first question we might ask, does this make any sense at all? Are there reasons to think that interactions with the lateral boundaries can play any kind of a significant role whatsoever in either the energetics budget of the ocean or in a potential vorticity budget of the ocean? So we do something very simple-minded. We turn on a general circulation model with extreme resolution just to see what kind of characteristics the flow in the presence of realistic topography has. This is a calculation that was performed by Professor McWilliams and Jeroen Mollemaker at UCLA. This is the west coast of the United States. The Monterey Bay is here. Here's the Monterey Bay Canyon. So this is a simulation which we've obtained by means of a series of downscaling efforts. So we started with the UCLA 1/8 of a degree pan-Pacific solution. That set the boundary conditions for an embedded numerical solution, which we continued to telescope to ever finer scales, zooming in on this particular part of the ocean basin. The advantage of this approach is that the model has realistic climatology to it. There's a well-developed and pretty reasonable-looking California undercurrent system in this calculation. The resolution here is about 100 meters. So this is what we think of as, I think it's a well-resolved balanced flow calculation, in fact even including several components of unbalanced flow. So we turn it on, and what is it that we see? The California undercurrent is flowing along here. What this is relative vorticity normalized by the local Coriolis parameter that we're having a look at a depth of 250 meters. And what you're seeing is extreme vorticities here, negative vorticities coming up here, pockets of positive relative vorticity peeking out here from various places along the topography. The long and the short of it is that anything of interest in this calculation has a root in topographic interactions of the interior flow with the boundaries. So you can see that the current flowing along here is generating strong vorticities. Those can separate, and when they do, they move out into the interior. In fact, the relative vorticities here can have values of well in excess of local F. So we anticipate that these flows are centrifugally unstable once they move out into the interior, are capable of inducing diabatic mixing in the open ocean interior. They tend to recurve around, run into the boundary, generate vorticity of the opposite sign, again, well in excess of F. So pretty clearly, there's a lot of dramatic features going on here, and this gives us some indication that things of interest are happening at the boundaries. As balanced flow, realistic looking, quote, realistic, balanced flow with topography interacts with it.
Did that big anticyclone you started with originate by separation in the same
Yes.
sort of way?
Yes, it did. In fact, there's another one forming up here, and sometimes they'll join up with opposite sign sources of relative vorticity here, and then that'll give them some self-propagative tendencies. They move out into the interior. So, you're generating a lot of anticyclonic vorticity, primarily anticyclonic vorticity, at least at this time of the year in this part of the world, and that tends to invade the interior through vortex dynamics.
There are much tidal effects in this. Are there tides flow along this coast strongly?
This does not have tides in it. Okay. So, now, if you go to Paris, you go to really excellent restaurants, and the food there is going to be fantastic, all right? Now, that's kind of what that last simulation is like. And it's too much for me to digest. I can't handle it. So I'm more of a McDonald's, Burger King kind of guy, so I have to take a step back and do something a lot simpler and see if I can understand that. So this is what I've done with Professor Hogg from ANU. We've done our version of the Monterey Bay calculation, and it's far simpler. So what is it? Well, we decided to just take off one chunk of this major problem. Okay, interactions of balanced flow with topography. We put a wall here. Now what am I looking at here? We're looking down at a channel. So you have walls here, here, and you have a wall here. And this is at two different depths in the basin. This is at about 1,000 meters, and this is at about 700 meters. And we initialize a dipolar vortex at this location in the channel. And it's set up in such a way that the mutual interactions of the dipole are going to drive things towards the west and run them into the wall. So if you will, this is just a simple collision problem, not the Hadron Collider that we heard about last night, but nonetheless a collision problem in which we have this vortex running into the wall. And the question is, what's going to happen? So this is perhaps the simplest calculation that one can do, the balanced flow interacting with quote-unquote topography. Well, here's what the movie is. Okay, we started up, and you can see that by this point in time, it's developed into a nice dipolar vortex. Again, what we're plotting here is relative vorticity divided by F. This is an F-plane calculation. There's no beta, but it wouldn't make any difference. And you can see the dipole streaming its way towards this interaction with the wall. Now, a balance theory tells us what to expect. It basically tells us that as the vortex comes near to the wall, it should look into the wall and see its image. That means it will pair up with its image, and we expect the anticyclone to see a cyclone and march off towards the north, the cyclone here to see an anticyclone. The two will pair up and march to the south. That's the prediction from a balance theory of this kind of an interaction. And sure enough, the first stages do exactly that. The two centers come in, separate, and begin to move away from each other due to the influence of the wall. But then at this point in time, we start to see something unusual happening. And it's right here in this blast of red that comes off of the anticyclone. And note that we don't see a comparable thing happening for the cyclone. So let me play that movie again without stopping, and you can just see the whole thing. Here comes in the interaction, the two separate, and then blam, we get something of interest that's happening there. Now this is unexpected from a balance theory. That particular effect there is not something that a balance theory would predict for you. So what is it? Well, what I want to do next is show you what happens when this occurs in the temperature field, and I want to do it from the perspective of an observer standing here in the middle of the channel and looking towards the wall. Yes, sir?
Your wall stress-free.
This is a free slip boundary. Yes.
Yeah, that's important, isn't it?
Yes, it is. But we can come back to that point a little later.
Even when it's going off to the, I suppose that's the west, you can see that there's a little tiny boundary of yellow around that group. So it's already there.
Well, let me take a look. I'm not sure what you're.
You see?
Well, by
Makes sense.
A little bit, yeah. I don't think that you're going to remember too much about that in a minute when we go to the next view, okay? Everything up to the point where they get this bread blob is something that's purely consistent with balance theory. Okay, so now here's the movie looking at the temperature. Okay, so here's the cold stuff at the bottom, hot stuff at the top. These contours are lines of constant temperature as the colors are. And so this is now an animation of what happens at the point when the vortex hits the wall. This is right at the point of contact with the vortex and the wall. The anticyclone is going to move in this direction, and the cyclone is going to move in this direction. So we'll turn the movie on, and for a while you don't see much. But then you start to notice a dippling occurring here in the isotherms. This is somewhat unexpected. And as it continues, it actually grows to quite large amplitude, and in fact, at this point, you can see evidences of overturning. So we've actually inverted the density surfaces on the wall, and it's at this point when that blast of red occurs. And then it kind of marches along in a nice sort of smooth fashion after that. And nothing happens over here. So that's kind of interesting, and run it one more time just so that you can see the whole thing take place. There's some kind of intensification of the wall response, boom, some overturning, and then a marching along almost in a quasi-steady state sort of fashion.
So the PV anomaly would be right in the middle, at middle altitude.
Yes, right in there. That's in fact where the red came from.
Of course, balance theory will distort your isopycnals, but your
Not
point is
too
not
much.
really so much.
The QG theory would predict that the isotherms don't change at all, that they stay perfectly flat.
Ooh, but if you add the deep side EZ, you know, if you add the leading order disturbance, they've got to bend a bit, you know.
But not like that. I mean, this is something that a balance theory would
I think
predict.
that's your point. This was not
Yes.
really as much.
Again, if you used SG rather than QG, that gives you a much bigger reaction for anticyclonic vorticity, and then it sort of pretty so it probably will end up not being balanced. But I mean, it's telling you get a bigger response for anticyclone than cyclone.
Well, this is true, but I think the semi-geostrophic theory might predict symmetric response between this, or anti-symmetric response between the anticyclones and the cyclones.
No, we've got this variable calculus. When it's anticyclonic, you've got a sort of very small number multiplying response, so that won't give you a symmetric response, but it will probably produce something that will then become unbalanced.
Fair enough. Moving along. Everybody hates that simulation for the reason that the real ocean doesn't have vertical walls. So we would like to know what happens in a more oceanographically relevant setting, which has more interesting topography. So we repeated a similar experiment where we did some kind of non-trivial topography with a slope and with lateral structure. And I might also add, this is a calculation which is motivated by the physical system of MEDIs, which are eddies, subsurface coherent vortices generated by the Mediterranean outflow. They form up into dipoles, they march off to the west, and they run into a series of topographic features, the seamount chain, horseshoe seamount chains, Great Meteor Seamount, which is just near the Azores. So this particular calculation has some quote-unquote relevance to the open ocean. We took the parameters for the seamount here and for the vortices from that system. So this is meant to be somewhat realistic, quote-unquote. Now this is a Gaussian seamount. We're seeing it here at a depth of about 1,000 meters. If we went deeper, it would be broader because it does have structure to it. This is the vortex which we run into the mountain. So I just have a simple movie here to show you that we can really do it. We pop the thing off in the direction of the vortex of the seamount, and boom, it runs right into it. Okay, so now, what does this look like? Well, I'm going to now show you an animation of the temperature field, again, from the perspective of a viewer standing about here and looking back at the seamount. And that's what's the next overhead. So here we are. We're looking back towards the seamount. There you see it off in the distance, and it's leaning away from you, as I've just explained, it being Gaussian. This surface is a surface of constant temperature in the fluid. It's roughly at the midplane of the dipolar vortex. And so What we're going to do is watch what happens on this surface as the vortex comes sweeping around the topography in this direction. There's some hint of it just beginning now. There's a little dimple right here. It doesn't show up very well. But now we're going to see the evolution of this thing in time as the vortex comes through. And you can see that what it does is steepens up rather dramatically and then bam. So what it looks kind of like is like a wave coming on the beach, where the wave comes up on the beach and deposits heavy water, which then runs down the beach and back into the ocean. And when it does, it joins onto its original isopycnal and radiates a large amplitude wave. So there it goes again. Boom, splash, big wave generation, radiation out into the interior. So we interpret this as evidence that the same thing is happening, in this case, as is happening on the wall. On the wall, on an isopycnal, the isopycnal steepened and overturned. In this particular case, the same thing happens. You see steepening, but now as the steepening occurs, it has to occur in a geometrically more complex situation, so the heavier fluid is now deposited uphill rather than straight above. And then once it does, it can cascade as a gravity current down into the interior, run into the isopycnal, and radiate off as a finite amplitude gravity wave. So we contend that the calculation up against a vertical wall is showing us dynamics which are representative of the general problem and not special to a vertical wall. So we think that we're seeing things of interest going on for this problem in which we're allowing a balanced flow to interact with topography in the simplest possible question.
Is that a two-layer model or multi?
That was a continuously stratified MIT GCM solution. And by the way, in the previous calculation on the wall, we showed that was run in the non-hydrostatic mode. But we could also run in hydrostatic. It doesn't make a lot of difference. The hydrostatic mode has implicit diffusion, or excuse me, implicit diffusion in it, and that seems to work pretty well to replicate the features. But just for purposes of being clean, we've done these calculations in non-hydrostatic settings. Okay, so the question I want to ask now is what's going on here? And that's going to be the subject of the rest of the talk today, in an attempt to analyze these calculations so that we understand what it is that we're seeing, and then maybe we can take it to the next step, which is to begin to talk about offering up a parameterization. Okay, so what I want to do is to develop as general a possible theory of interactions with the wall. And because a wall is more simple to work with than a general topography, I'm going to start with the case of a vertical wall, appealing to the numerical calculations to argue that there's relevance of these dynamics more generally speaking. So we always have to start with some equations. What are the equations we're going to use? They're listed here. These are the well-known momentum equations, two momentum equations here, continuity equation, and hydrostatic equation. Now, these are familiar. The one distortion to them from the way we normally think about them is that I've written these in density coordinates. But I believe everybody here is very familiar with that technique of looking at the dynamics. Full momentum, we require here in the place of pressure, which would be present in a Cartesian system, the Montgomery potential, which is written here. In density coordinates, one of the predictive variables is the depth at which isopycnals occur. The independent coordinates are x, y, and density. Z as a function of density is something that you calculate. Where in the water column is the density surface? The continuity equation looks like this, in which, if you think of the more familiar instance of multiple layer models, primitive equation models, you would call dz rho h, layer thickness. So dz rho takes the place essentially of h. So it's a simple continuity. Straightforward manipulations of these equations in familiar ways lead to a potential vorticity equation, which I'm showing here, with potential vorticity, the full Ertel potential vorticity compactly written in this fashion, all derivatives being taken on density surfaces. So it just simply says that we're going to materially conserve potential vorticity on density surfaces. Now, a few things. I have, for the moment, neglected any frictional processes which would sit on the right-hand side of these equations. And and I've neglected any diabatic processes which would enter here in terms of a cross diapycnal flow. But we'll come back to consider those in a bit. They would have a presence in the potential vorticity equation lining up as the so-called the divergence of the so-called non-advective fluxes that one would see for potential vorticity. All right, so those are the full equations. They're accurate to the full hydrostatic approximation. So they're quite accurate. Now, we start doing obvious things. We take these equations and we go to a wall where we have a no normal flow boundary condition sitting here, and we just do the obvious thing, which is start crossing off terms in the equations which have to vanish on the wall. So in one of the momentum equations, by throwing away the presence of u, we find that we simply have geostrophy. So this is the normal to the wall momentum equation. It leaves us with geostrophy and nothing else. Now, there's no small Rossby number approximation in that. That's just a result of the no normal flow condition. The other momentum equation also simplifies considerably so that it's now essentially a 1D equation on the wall as a function of density. Very simple first order equation. Potential vorticity is also somewhat simplified. We can drop the normal advection of potential vorticity, and the form of potential vorticity itself simplifies somewhat because we can neglect one of the components of relative vorticity. Now there's a consequence of this equation. What it's telling you is that you can't really import potential vorticity onto the wall. So if you think about the initial value problem that we were just talking about, you have some balanced flow in the interior characterized by some non-trivial potential vorticity, and it comes running towards the wall. Well, that non-trivial potential vorticity can never actually get on the wall. It has to stay physically separated from the wall because there's no normal flow. So the response on the wall has to be governed by whatever potential vorticity was there initially. And in this initial value problem, we can make the assumption that we have initially a resting flow that corresponds to a zero potential vorticity anomaly state on the wall. And if you work out what that has to look like, you find that the potential vorticity on the wall has to take this form. This now becomes the equation for the potential vorticity anomaly on the wall. So we essentially have here a dv dx because of geostrophy. So that's a relative vorticity contribution. And then here's, because the second derivative of m with respect to rho is proportional to thickness anomalies, this becomes the statement of thickness anomalies and potential vorticity, and we adjust for the background state, which is appearing here as m bar rho rho. That's a statement of the background pre-existing stratification on the wall, which defines the background potential vorticity statement. So the wall response has to be governed by that. Now, this is dangerously close to being accurate to the full hydrostatic equation. So there's no small amplitude assumptions built into this. And so what we have is the opportunity to calculate something extreme. This set of equations is extremely simple. And we can calculate it and use it as a model for the response on the wall at finite amplitudes. Now the picture that I'm thinking of is something like this. You have an impinging non-zero potential vorticity blob out in the interior. That's our balanced flow. That's related to, you invert an elliptic equation in order to get the dynamic fields associated with the balanced flow. That's a non-local process. So the non-zero potential vorticity anomaly here kind of beams its response, and some of it will manifest as non-trivial fields on the wall. So this is going to visit an effect on the wall. And the wall has to respond, and it has to respond in such a way as it's obeying these equations. It's really the only physics in this calculation is the decomposition between a balanced flow in the interior, which radiates onto the wall, and a wall response. It invites us to take velocity and decompose it into both a wall response, which I'm calling V prime, and a VG, which is the balanced flow expression on the wall itself. So taking those simple wall equations and rewriting them with this decomposition, here's what we've got. These three equations. And if you will, this is a finite amplitude theory of wall response. And it's like, it's ridiculously simple. It's a shock. And so, in fact, these three equations fall into a very special category of equations, very small category of equations. And those are simple enough that even I can solve them. And believe me, that's a very small category of equations. But it's really trivial. Look at how it works. It's an initial value problem. So let's suppose at some time we know a v and an m. Could be 0. The far field is going to radiate a presence onto the wall. You can solve this equation to get a new value for v. But that new value for v, by this equation, is simply dm dx, which is the normal derivative of m with respect to the wall. We come down here to this elliptic equation. To invert this requires boundary conditions of either the Neumann or Cauchy type, and what we have is Neumann conditions naturally from the solution of this equation, so we can write down the unique solution of this equation. That gives us a value for m in the future. We can then go back up here, differentiate the m, and now we're in position to do this again, to iterate. And so now you can turn the crank as often as you like and predict for finite amplitudes the response of the wall to this disturbance. And this looks like it's dangerously close to being accurate up to the hydrostatic bounds. Okay, so what you then do is you solve these equations, and we've done that numerically, and you ask whether or not it works. And I wouldn't be here talking to you if it didn't, so you must know what the answer looks like, and that is that it basically does work. We compare the solutions predicted by this very simple theory to the solutions from the MIT GCM, and the long and the short of it is that many quantitative measures are accurately captured, things like rates of development of the disturbance, the structure of the disturbance, etc. So we're satisfied that we have a surprisingly accurate model of the full MIT GCM primitive equations, but again, it's a trivial set. Now, as an example of that, let me show this, which one of the most interesting things that we saw before was the cyclone-anticyclone asymmetry. That's what I'm showing here from the MIT GCM solutions. These are the isopycnals, and you see the steepening here. And what the colors here now are velocity. Okay, so this is the anticyclonic velocity. You see it's taking a wedge shape. For the cyclone, you have southward directed flows. That's what the blue is showing you, and you see that everything is pretty calm here for the cyclone. So this is the asymmetry that was noted between cyclones and anticyclones, and that's captured in the model. Here is a northward propagating anticyclonic flow at day 0, and this is what it develops into at day 4. You can see a wedge shape. This is only the velocity. So you can see that the velocities develop into the wedge shape, which you're seeing here. And there's some indication of intensification, some indication of instability in the sense that the values of these velocities have grown beyond what they started with, which is also characteristic of this. This is a southward moving cyclonic disturbance on the wall, and at day 4, here's what you get. There's no indication of intensification at all. Basically, the symmetry, the initial symmetry of the structure is retained. There's not much of interest going on here, and that's largely what you're seeing in this calculation. So the asymmetry, which appears from the numerical calculations, is appearing in the very simple model that we have. Now, the advantage of this is that we can, with this new set, thinking that we've actually got something that's telling us about the system we're seeing, we can analyze these equations. And these are a whole lot simpler to analyze than the primitive equations. So you have a hope of beginning to understand what it is that you're seeing. Okay, the first question we might want to ask is, why is the response asymmetric? Well, we look at the equations we've got here. And the way that you do that, and it does tell you the answer, interestingly enough, or it tells you an answer, which I am tempted to believe is right. Starting with these equations, we can linearize them, because you might ask, you're seeing the asymmetry very early on before the response is finite amplitude, so linearization seems a sensible thing. And what you find is that this equation becomes this one, with the geostrophic velocity in it. What you're seeing here is, if you had no geostrophic velocity at all, that would be 0, this would be 0. You're seeing an equation for Kelvin waves. Well, okay, this isn't a surprise. Kelvin waves on walls. But what that's doing is it's telling you that the response is going to largely be asymmetric between a cyclone and an anticyclone, because Kelvin waves always want to move to the south. So if we have a picture of velocity as a function of position on the wall, if you have an anticyclonic flow or southward flow, it will be negative. Cyclonic or the anticyclone will be positive on the wall. The Kelvin wave speeds are always one-signed. And so clearly, if you have a non-zero geostrophic flow, the contribution of this equation, of this component of the equation to the evolution of the system is going to be different for the anticyclone than for the cyclone. So we expect there to be an asymmetric response. Okay, so the asymmetry is because of the preferred direction imprinted on the system by the wall. What else can we say? Well, we can ask about the sources of the instability. Recall that there was evidence of instability processes going on because the velocity field was amplified in the evolution relative to its initial values. Well, what's the source of that instability? We can linearize and look at the velocity field first as a function only of density. Everybody thinks baroclinic instability is a process of considerable importance in the open ocean interior, and it is. So your first thought might be that any instability going on here is likely to have a baroclinic source. So you'd like the velocity field to depend upon density, giving us a baroclinic potential energy source. Ask for the velocity to be a function only of density, linearize the equations, and you can play around with these in a manner that's reminiscent of what happens with the inflection point theorem, and demonstrate that under no conditions will this set of equations permit there to be instability. So at least in the linear sense, we can rule out the baroclinic source of energy for any instability that's going on. So that doesn't seem to work.
Did you mean balanced baroclinic instability?
The VG is itself a function of rho. So I mean, anything that happens here is happening because the flow is coming onto the wall. So any energy that's driving anything has got to come from that initial energy source, which itself is the balanced energy. And so that, in this case, we just say VG is a function only of rho for the purpose of investigating that type of flow. Now we can also ask, what about barotropic sources? Barotropic sources are those in which there is some kind of lateral shear. So in that case, the impinging flow is a function of position along the wall. And in this case, we actually get something pretty interesting. Okay, if you linearize and require that VG be only a function of y, the equation that you get is again this one, okay, which we saw before, in which there is the presence of Kelvin waves involved as well as a geostrophic flow. Now, Kelvin waves, as a general rule, we tend to think of them as fast. The first baroclinic Kelvin wave moves at a couple of meters per second. By oceanographic standards, that is quite fast. However, that's not the only mode there is. There are as many modes as you care to calculate, and they're ordered in such a way that higher and higher modes move successively slower and slower and slower. And in fact, eventually, no matter how slow the geostrophic flow is on the wall, there will be Kelvin waves that move slower than that. So they are able to interact at leading order with the geostrophic flow. QG theory neglects this entirely. QG theory says the Kelvin waves move so quickly, no matter what, that they move out of interactions immediately with the geostrophic flow. That's true for the baroclinic first mode, but it's not true for higher modes. So, again, appealing to this picture, here's position on the wall and velocity, and we imprint on it a geostrophic vortex, cyclone-anticyclone pair. The first mode is faster than any velocity we expect to be seeing, but as you go to higher and higher modes, those velocities drop down, and now, down in here, you get places where the Kelvin wave speed actually matches the geostrophic flow on the side of the Kelvin, on the side of the anticyclone. Now here's the equation that we get. At such locations as that, this term identically vanishes. And what we then left with is an extremely simple equation, which permits exponential growth or decay depending upon the details of the geostrophic flow. If VGY is negative, then you get growth, and if VGY is positive, you get exponential decay. BGY being positive is a place like this. So what's happening here is, if you think about being at this critical location, and you have a bit of a disturbance on this side and a bit of a disturbance on that side, here the Kelvin wave is, if I got this now, the Kelvin wave is slower than the geostrophic flow, so the geostrophic flow pushes it to the north. Here, the Kelvin wave is faster than the geostrophic flow, so it runs off to the south. So those two disturbances at that point separate. And that's a location where you have exponential decay of the disturbance. Over here, however,
Hang on, the Kelvin wave can't go to the north, can it?
no, but the combination of the geostrophic flow plus the Kelvin wave can.
Oh, it's enslaved.
Yes, the Kelvin wave is in the midst of a geostrophic flow, which is moving around. So the Kelvin wave is trying to swim upstream, but it can't because the advecting flow is too strong.
It's swept
So it's-
backwards.
Yes, that's right, swept backwards. Here, however, the opposite happens. Here, the Kelvin wave is slower than the advecting speed, and so any disturbance on this side of that critical point gets pushed into that location. Over here, the Kelvin wave is a little faster than the flow, so it also converges on the same location. So you get this convergence of disturbances, and that's associated with exponential growth. So locations like this are places where we expect to see finite amplitude results appear. And if you will, that's the source of the instability. It's a long wall shear, and the mechanism is one of arrested Kelvin waves. The Kelvin waves are trying to swim upstream, but at certain locations the high mode waves cannot get through because the advecting field countering them is too strong. And they get trapped at that location, and there's an explosion of growth. And you can't avoid this. Doesn't matter what velocity you put on the wall, there will be Kelvin waves slower than that. So this is always going to happen. So that's that component of the analysis. But we can even take it further. We can ask, what does the nonlinearity do in this case? We have finite amplitude equations. We can analyze those. And interestingly enough, you can do that analysis. This is aided by stepping back for the moment and going to a reduced gravity frame, where you artificially work with a small deformation radius to mimic going to a high mode Kelvin wave. But in that case, you have a set of equations which are not that hard to solve. This is only a first-order quasi-linear equation, and you can solve it by the method of characteristics. And what you do there is you figure out the characteristics paths in which initial value information is going to follow. That's what's shown here. Down here is time 0. This is location along the wall, and as time progresses, we move up the axis here. And what this is showing is what the characteristics are doing. This is inside a geostrophic flow that's actually piecewise linear, which makes this analytically amenable. So the characteristic here, which starts at one side of the vortex, wants to move nice off to the south, just like we expect. But eventually you start seeing vortices that the advecting field is able to sweep upstream. Not vortices, but trajectories that the advection field is able to sweep upstream. And in fact, here's the location of linear arrest. This is the place where the velocity matches the amplitude of the eigenmode for the Kelvin wave. But you see that the characteristics don't end up there. In fact, what happens at finite amplitude is they knock the wave off of that point of linear arrest. So this is why things stop their exponential growth, because the nonlinearities detune the evolution away from the point of exponential growth. You start to go to finite amplitude, and then the response is able to move off of that location because of its propagative characteristics. Nonetheless, the characteristics still focus, and the prediction is, in general, you expect there to be a place where the characteristics join, and in classical characteristics theory, this is a place where we see a shock. Such locations have to be treated specially. But given that, going back to our original calculations, I would like to argue that that's what we're seeing here. You're seeing a shock form up, which then propagates along in nice, simple fashion as a shock. And that's, I'm arguing, the result of this steepening and characteristics formation, shock formation process. Now the equation is simple enough that we can actually calculate how fast the shock has to go. And just do the calculation in the usual way, looking for the weak solutions of this equation. So you integrate across the front and you get the straightforward kind of formula that you would expect for the shock speed. And it has a pretty straightforward interpretation in terms of c is now the speed at which the vortex is moving. So the vortex advection is right here, and the propagation characteristics of the front itself are right here. So this is a Doppler shifted front. But because of the theory, we know an awful lot about this information. We know the values of the Montgomerys that are being delivered at both sides of the front from the macro theory. The large-scale theory is telling us an awful lot of information about the structure of this shock, and therefore constraining strongly for us how fast the shock can move. Now, so at this point you do something really crazy, because why not? You go back to the equations and you say, you know, what does a potential vorticity field look like? What's the evolution equation for potential vorticity if I don't ignore those terms like friction and diabatic effects? So you write the equation out fully, and here's what it is. So here's the frictional components coming in here. Here are components that are due to the diabatic effect. What this is the net effect on the right-hand side of the density field, this capital H. Suffice it to say, these are the diabatic components and how they end up manifesting as changes in potential vorticity. And then you do something pretty straightforward, because this is written in this conservation form, the flux form. You volume integrate it over an area which surrounds the shock, where the shock occurs. So that's what I'm showing here. Here's the offshore geostrophic flow. Here's the wall, and you volume integrate like this in such a way that you're enclosing the location of the shock, the horizontal plane, and going out far enough that you're actually out of the location of the shock. And in the vertical, you look at density surfaces that are around where things are happening. Okay? And you're tempted to say that by the time you get down to here, where things are pretty boring, that any diabatic or frictional effects are weak. Up here, you say the same kind of thing. So all the action is happening inside this volume. And you make the claim that the theory you have is quite nice right up to the point where you get overturning. So you're quite happy to live with the Inviscid and adiabatic theory up to the point where you get to here. Then all kinds of stuff start happening. In particular, we anticipate, and I'm making this assumption, that diabatic effects are in control of the non-conservative processes, and principally I say that because of the overturning that takes place. If you integrate this equation over the volume, a bit of magic happens, and what you find is the result of it all is this equation here, which relates the flux of anomalous potential vorticity through this face of the control volume, the total flux of anomalous potential vorticity, to processes happening on the wall. And of those, I've selected the diabatic processes. But the point is that we know an awful lot about these, because we know how fast the front is, how big it is, what densities are participating in it. We can estimate how big the shear is from the structure that's imprinted on the solution by the large-scale adiabatic Inviscid theory. So we can estimate this integral, and we end up getting a statement about the scaling law that governs the flux of anomalous potential vorticity into the interior. Now, to my mind, this is beginning to get very close to a parameterization. And let me just, I don't think I've got, yeah, I don't have the, I'll have to step back a little bit, sorry. It's also what I think is going on here, that anomalous PV flux. It's what we're seeing happening right here, boom. That being relative vorticity divided by F, it's very close to what you would see if you looked at potential vorticity evolution as a function of time on this density surface. And so that is the injection of anomalous potential vorticity by these wall processes into the interior. and it's opposite sign to the structure of the potential vorticity and the impinging vortex. It's a dissipative process, necessarily so. It's also sizable. We did an order of magnitude estimate of the anomalous potential vorticity in here relative to that, and it's several percent. And so this is a reasonably dissipative process. And so what we have is something that's perhaps close to the situation where we think about interior geostrophic flows interacting with a flat bottom, in which we set up a bottom Ekman layer, which induces a pumping into the interior that spins down the interior geostrophic flows. That's a case where the boundary problem has been solved, and we no longer have to explicitly calculate the boundary flow. We can just calculate its effects on the balanced flow. We're close to that here. You run a balanced flow into a lateral topography. We now have a formula that tells us about the anomalous potential vorticity that interaction wants to inject into the interior. And then that is something that we could think about using as a parameterization of this process in a balanced flow model, so we don't have to explicitly calculate this. So I'm trying to interest Pavel in that, but he doesn't like the idea. And I can't seem to get him to work on it with his model, but we're trying. And I also wonder if this is something that we can figure out some stochastic parameterization for in a non-eddy resolving model. Now, there are lots of other things one would like to talk about, including can this be extended to non-wall topographies? And I'm guardedly optimistic that it can. I'm hoping to have a few discussions about this week with people who are here who are experts in these kinds of things. But I believe that I have a way of extending this to more general topographies. And then we'd like to experiment this with models, which that has not happened, but it is hopefully to come. So with that, I've finished my hour. I understand there's a seminar that's coming up in a little bit, so I better stop, and I hope I can answer any questions you might have. Now my blood is going to run freely in the streets.
No, not at all. When you say stochastic parameterization, you don't mean a stochastic differential equation, you mean stochastic boundary conditions.
Yeah, that's right. Mm-hmm. That reflects this process. I mean, you should be able to constrain the strength of it, given information about the interior. Because whatever the interior wants to impart on the wall controls the structure of the response. So you'll have information about the near wall flows, and that should be able to tell you about how you should pop up bits of anomalous potential vorticity into the interior on the wall.
A comment, really. In this business of generating your sort of captured shock-forming Kelvin wave, it's in some ways a bit reminiscent of these dipole examples in continuous stratification that have been put forward by Schneider, Plugonvent, Miraki et al. And Vudeth. You know that work? In which you've got a dipole in a pair of PV anomalies going along in a continuously stratified. You get quite a close coupling with the gravity wave field, again because there's always some modes that are slow enough. In all these problems, yours too, I think, the spontaneous imbalance is exactly outside the sphere of Lighthill theory. Of course, in your case, there's another reason too, which is you've got a boundary which can exert forces, but I think that's slightly a red herring. And I feel I have to go around saying this because I thought Lighthill had it all for quite a long time, and he does if you're in a shallow water world, but not in these continuously stratified problems. So I think your problem's another rather interesting new example to add to that non-Lighthill repertoire.
Okay.
Sorry. I asked a question raised at the beginning of the talk, which might give us some clues. So you said the fundamental issue was that the atmospheric circulation much stronger winds than the ocean can catch up with, so it tries to spin up, and at some point it reaches. So at some point the dissipation balances the spin-up effect. That's the sort of thing I'm trying to explain. Now, presumably, this circulation that spins up is essentially, large-scale circulation is essentially geostrophic. So is there do you reach some limit where you can't supply the mass field to support the geostrophic balance, and then it just can't spin up anymore because you can't generate mass field, and therefore things have to become unbalanced in rather more fundamental ways? Is that part of what's happening? You can't really imagine the ocean currents actually keeping up with the wind force on those. It's just completely a possibility. So at some point, you try and
if there were strictly speaking no dissipative processes involved, then it could.
well, it couldn't be geostrophic because you could never the mass field to support that just isn't available.
It could still accelerate. I mean, it does. You're right. You may end up getting into a situation in which the Rossby numbers are no longer small.
Then you're going to get something that's fundamentally unbalanced, and the balance could break down because you can't. And then it's so. Wondering how that sort of fits into the picture, because I would imagine that you just can't get a geostrophic response in the ocean above a certain amplitude. And any further spin up has to be in balance, essentially.
That's true, but I think the situation we're in is the one in which basically we are in geostrophic balance, and so whatever dissipative processes there are.
That presumably is saturated. It's got as strong a circulation as it can get while being geostrophic, and then essentially on the inbound.
Well, that's not the experience of numerical modeling, right? In numerical modeling, if you have if you have too weak of a dissipation, then you spin up a stronger flow that's largely geostrophic. It just becomes unrealistically large, but it's still largely geostrophic. People call that the runaway solutions, but they're still basically geostrophic, and they find a way to get to be, by basically nearly symmetric flows to be largely geostrophic and very high amplitude. But they're not reminiscent of what people say.
Yeah, as you move to more realistic flow configurations, have you thought about what the effects of having a western boundary current, for instance,
Yeah.
these boundaries is to this effect?
Well, I think that basically what we have here in the vortex is just a metaphor for any balanced flow. So I think that the variability of a western boundary current as it bumps up against the continental slopes are places that are ripe for this kind of thing to be happening. And the western boundary current is well situated to have this going on because it's counter to the sense of the topographic wave propagation. And so this should be happening all along the western boundary current. Now, another important thing that needs to be brought into the theory is some further understanding of the effects of a turbulent bottom boundary layer. And I think that a lot of what we see in McWilliams simulations, especially where you have the northward flowing California undercurrent, is the effects of turbulent bottom boundary layer. That's ultimately the source of the vorticity that you're seeing there. But at points of separation, the current turns around and hits the topography. You'll see explosions there of cyclonic vorticity, and those are locations as the flow heads back south to rejoin and form up into the vortices that we see. Those are places where these mechanics are likely to be happening. And while I have not analyzed those solutions from that perspective, that's something that we're going to be doing soon. So I think that's what might be happening there. So I think these mechanics can kick in, even in the presence of turbulent bottom boundary layers and friction, which requires the presence of a no-slope boundary or a no-flow boundary condition.
You showed the recipe for PV flux generation on the wall, so it's proportional to F squared RD squared. Do you have a scaling for dissipation of energy, simple one, during this process? Dissipation of balance.
Yeah. No, not really. I mean, what I would think of doing is taking the anomalous PV and inverting that in some simple way, and then adding that effect in on the dynamic fields. And since it's of opposite sign, it will be such as to decelerate. So there will be an energy loss associated with that. I don't, but I haven't sat down and thought of an energetic scaling for that yet.
Okay. Thanks very much, Bill. That was fascinating. We've got another seminar scheduled for 1:15, but I'll ring the bell. We'll have a little break now, and I'll ring the bell when we come back.